Okay, in this chart we'll look at the scenario for a rocket on a puck and the puck on a frictionless ice rink. And we'll use free body diagram and Newton number 2 to analyze the problem. So let's say that we have a rocket that's mounted on a large puck and it's placed on a frictionless skating rink, and that the mass of the rocket and the puck is 1.5 kilograms. I'm essentially going to be taking the mass of the rocket and its fuel to be 0 and the mass of the puck to be 1.5 kilograms in this problem. Let's take the thrust of the rocket to be 0.75 newtons. First of all, let's draw an FBD, then we'll find the acceleration of the puck using the FBD and Newton number 2, and then we'll use either calculus or the kinematic equations with constant coefficients to find velocity of the puck 2 seconds after ignition and the displacement between 1 second and 2 seconds after ignition. So first of all, free body diagram. There are three forces acting on the puck. The normal force of the ice acting upwards, the force of the earth acting downwards, which is the weight of the puck, and the force of the rocket acting to the right. With our standard coordinate system, we have a Newton number 2 in the y direction, which says that the normal force of the ice on the puck minus the weight of the puck is 0 because the acceleration in the y direction is 0. And the Newton number 2 in the x direction says that the net force, which is, since there only is one force in the x direction, the force of the rocket on the puck is the mass of the puck times the acceleration of the puck. So we can solve that for the acceleration of the puck to conclude that the acceleration of the puck is the thrust of the rocket, 3/4 of a newton, divided by the mass of the puck, 1.5 kilograms, and that gives half a meter per second for the acceleration. So to solve for the velocity 2 seconds after ignition, we could take the constant acceleration and integrate it from 0 to 2. Constant acceleration is 0.5, and so the integral of that is just 0.5 times t. Evaluated between 0 and 2 is 0.5 times 2 minus 0.5 times 0, which is 0.5 meters per second times 2 seconds. In other words, it's 1 meter per second. Alternately, we could use the kinematic equations with constant acceleration, in which case we'd have the final velocity is equal to the initial velocity, 0 meters per second, plus the acceleration times the time difference, 0.5 meters per second times 2 seconds, which also gives 1 meter per second. For the displacement question, we can take the velocity function and integrate it from 1 to 2 to find the displacement. So integrating 0.5 t from 1 to 2 is the integral of 1/2 t is 1/4 t squared. Integrated between 1 and 2 is 1/4 times 2 squared minus 1/4 times 1 squared, which is 1 minus 1/4, which is 3/4 of a meter. Alternately, you could use the kinematic equation for the displacement, and that equation is initial velocity times the change in time plus 1/2 times the acceleration times the change in time squared. Be careful though, if we apply this kinematic equation, since we're going from time 1 to time 2, the initial velocity is not 0, it's 0.5 meters per second squared times 1 second, and so the initial velocity is 0.5 meters per second. That's what this is. 0.5 meters per second times 1 second, that's our delta t, plus 1/2 times the acceleration, 0.5 meters per second squared times 1 second. And so this is, this first term gives me 1/2 a meter. The second term gives me 1/4 of a meter. 1/2 plus 1/4 is 3/4 of a meter. Again, consistent with our calculus answer. Question for you. Perhaps you can redo this problem and find v 4 seconds after ignition. and also find the displacement between 4 seconds and 6 seconds.